Hi guys, my name is Famela.
I'm Monica.
I'm Princess.
Emker.
And for today's vlog, we are going to talk about the unreal reality of mathematics, Nature's Number Chapter 9 of Ian Stewart's book. So in this chapter, we are going to talk about the complexity, how complexity emerges from simplicity.
Ian Stewart introduced two different theories such as complexity theory, which central theme is that a large scale of simplicity emerged from the complex interactions of large numbers and components, and the theory dynamical systems, which is an area of mathematics utilized to describe the manner of the complex dynamical systems, commonly by applying differential equations.
Henri Poincaré, a French mathematician, was regarded as the founder of dynamical systems. These theories were used to further explain the math regularities in the examples that he proposed.
The examples that he proposed to further prove his claim of simplicity emerging from complexity are there is simplicity in complexity. Through the shape of water drops, the dynamic behavior of animal populations, and the strange pattern in a plant petal numerology.
So what are you waiting for? Let's start with the first example. The first example is about the shape of water dripping from the tap. Ian Stewart believes that this example shows his idea of complexity emerging from simplicity, because if we look into the details or the process of how the water drops off the tap, it becomes so complicated that the simplicity is lost. This is actually an everyday phenomenon, yet it has shown us or taught us about chaos, and now it will teach us something about complexity. In this example, we do not focus on the number of drops it takes, but we focus on the shape that it forms as it detaches from the end of the tap. As obvious as it is, one look and we can say that the shape of the water droplet is in the classic form of a teardrop, round at the head and curving away to a sharp tail. What's more fascinating is that it is actually not its true shape. And we believed this lie for a very long time. Also, did you know that the early literature contains only one correct drawing of it? Did you know who drew it? It was made over a century ago by the physicist Lord Rayleigh or John William Strutt. He is an English physical scientist who made fundamental discoveries in the fields of acoustics and optics that are basics to the theory of wave propagation in fluids. Isn't it amazing? The water droplet is very small, and he was able to draw its true form. What a great physicist!
So today I'll be talking about Chapter 9, second example, Population Dynamics. What is population dynamics? So population dynamics reflects a long tradition of mathematical modeling in which the changes of population of interacting creatures are represented by differential equations. In 1994, Jackie McLeod, David Rand, and Howard Wilson of Warwick University carried out a fascinating study that bears on the relation between more biologically realistic models and the traditional equations. They created a game that follows a strategy common in complexity theory, that a system of rules is set up to model the main biological influences at work. McLeod's group played a more complicated game than this, but you get the idea. This is where McLeod's group made a dramatic and surprising discovery. Differential equation with only four variables captures the polar features of the dynamics of the rabbit population, with only a 6% error despite the far greater complexities of the computer game model. This discovery implies that models with small numbers of variables be more realistic that, than many biologists have hitherto assumed. Its deeper implication is that simple large-scale features can do and emerge from the fine structure of ecological games. Bye guys!
The third and final example of Ian Stewart is the mathematical regularity of natures that emerges from complexity rather than having built in with the rules is the number of petals of flowers. He was aware that majority of plants have a number of petals taken from Fibonacci sequence. Also, it was stated that some features of morphology of living creatures are originated genetically and some are products of physics, chemistry, and dynamics of growth. Living organisms have complicated DNA sequence that determine which proteins are made of, and so on. It doesn't follow that genes determine everything, and even if they do, they may do so only indirectly. For example, genes tell plants how to make chlorophyll, but they don't tell the plant what the color of chlorophyll has to be. If it's chlorophyll, it's green, there's no choice. A lot of observation and studies were performed to know how these flowers were able to have that certain sequence of numbers seen in their petals. And one of those people are Dowdy and Cowder. They built their ideas upon important insight of Hermann Vogel. His theory is again in a descriptive one. It concentrates on the geometric of arrangement rather than on the dynamics that cause it. He performed numerical experiments which strongly suggested that if successive primordia are placed along the generative spiral using the golden angle, they performed an experiment using circular dish full of silicon oil placed in a vertical magnetic field. They let tiny drops of magnetic fluid fall at regular intervals of time into the center of the dish. The drops were polarized by magnetic field and repelled each other. They were given a boost in radial direction by making the magnetic field stronger at the edge of the dish that it was in the middle. The patterns that appeared depended on how big the intervals between drops were, but a very prevalent pattern was one in which successive drop lay on spiral with divergence angle very close to the golden angle, giving a sunflower seed pattern of interlaced spirals. Dowdy and Calder also carried out computer calculations with similar results. By both methods, they found that the divergence angle depends on the interval between drops according to a complicated branching pattern of wiggly curves. Each section of a curve between successive wiggles corresponds to a particular pair of number of spirals. The main branch is very close to a divergence angle of 137.5 degrees, and along it, you find all possible pairs of consecutive Fibonacci numbers, one after the other in numerical sequence. The gaps between branches represents bifurcations, where the dynamics undergoes significant changes.
In conclusion, simplicities do not present themselves directly. Instead, clues were hidden everywhere to be seen by mathematical detectives to solve the puzzle of the mystery of the mathematical regularity. That there is a more common thread, an even deeper message buried within.
My insights about this chapter is simply stated that mathematics, its nature is simple. We are just looking beyond much difficult way to will become chaotic. This explains that we are the one who see mathematics difficult because we people itself go beyond a certain topic. Well, in case mathematics is simple in its own way.
My insights about this chapter is every simple thing has complicated ways. With chaos in mathematics, we barely see simple things and find it complicated. The complexity theory taught us that simplicity tends to disappear when we look below the surface. But in the surface, it is still there. As systems exhibit chaos if it has solutions that appear to be quite random, and the solutions exhibit sensitive dependence on initial conditions.
I actually learned a lot from this chapter. Everything was very informative and in details. I like how Ian Stewart based his idea of complexity emerging from simplicity in those three phenomenon that really happens in real life. All in all, I think that the mystery of simplicities could be found everywhere and anywhere. They are just waiting to be solved and discovered. And I think that the point of the author is to appreciate every good and even the bad things in life, because there is so much more beyond it. That there is a certain reason why a certain situation happens or a certain thing behaves or looks different. So that's it for today's vlog, guys. I hope you have learned a lot from our insights, from our examples, or from the book itself.
Bye and thank you.
Thank you for
Bye,
watching.
guys.
Bye.
That's all, folks.